Yeah.
So I might be at the Vmax here, or it might be at 150. Let's assume that we thought it was here and see how far we'd be off compared to if it had been somewhere else. If I thought it was here, this was the Vmax, what would I evaluate for determining the actual Km?
1/2.
Tell somebody else what number you would be listing as the Km value.
So
Yeah.
I was confused. Oh,
You're right.
concentration.
You're right.
Oh, so I
So
think
I think that's the change.
15. But then I
Like
just wrote
from
down
the
75.
original
I think that's
case,
down. Like we can go from 75 concentration to
So
approximately
1/2 of Vmax, 1/2 of
like 85.
this would be 45, which would be between 15 and 20, right? And so it'd be really close to 20. But I'm not listing this number, I'm listing this number. What is this? Substrate concentration. Remember that when we derived it, that the 1/2 Vmax, the Km, was at the substrate concentration. That's where it's read. For whatever silly reason, that's where we're reading. Now, if I had done 150, what would it change? I would have jumped it up to
50.
Sorry, that would have been 100 here. I would have gone to 50. I would have been maybe 21, 22. So if that was on a multiple choice, I'd have to be really nitpicky to have. I don't have to be that nitpicky. You're gonna know it or you're not. What's somebody gonna fall for? They're gonna give me this number, aren't they? Yeah. Somebody's gonna give me the Vmax. Somebody's gonna read half of this and try to go over here. It's gonna be.
That's what I tried to do.
Do you see how easy it is to mess on something that's really easy? You know, like I could do that, right? So, and then that's Vmax that we would be assigning and a Km. And then it says determine the Kcat in units of per second and specificity constant. So how did I calculate Kcat again?
It's Vmax over the enzyme.
Vmax divided by the total concentration of the enzyme. From this, I know the concentration is in micrograms per liter, and I want it in molar. I could take and divide that number 10 times 10 to the negative 6 by that number, and I would know the amount in molar that I was interested in. And then I would also use the Vmax I just got to determine that. So when you're looking at that, that is what we're doing. We're getting that value. Now, this is plotted to get that sort of value, okay? Where was the real values, right? It was 101, by the way, for the real values. Okay? But then you can turn around and get the concentration of Vmax per second. Kcat is Vmax by enzyme total, so you can calculate those. And then you can calculate the specificity constant by doing what? Take the Kcat and the Km. What's the affinity? What's the how fast it's turning over? And you want a big number there, which means that having the Km in the denominator makes it big if it's doing a good job. Because what makes an enzyme good at finding the substrate? A high Km or a low Km?
Low Km.
If the Km is low, it has a higher affinity for the substrate. Make that note somewhere if you don't know that. That's not intuitive to you yet. Make a note of that, okay? It means it went faster on that curve at a much lower concentration. That's what it's saying. Okay. Now, all right, let's look beyond that. So, any other questions on this part of chapter 6 that we've looked at? You guys feeling it? Okay.
I do want to confirm
Yeah.
that for the Vmax,
Yeah.
we have units. Oh, it's I missed the micro. That's why my numbers are all off. It's micromolar, and you have to convert it back to molar.
Okay. So the other piece that we should look at, right, is making sure that we looked at this study guide, knowing that that was really the key to the exam, right? So we look at study guide for 3.1, and check out if we're doing all right here. So, vitamins, dietary precursors, coenzymes and cofactors, and okay, understanding that. Reactions, 7 classes describing them. Did you review those? How does the enzyme have a rate of reaction versus the free energy change of that reaction? We've talked about that. We've taken questions. Information about stickase. What information can we get about it? Energy barriers that the enzyme is overcoming there. And remember, we described it's able to find the substrate, coordinate the substrate, push them close together. It's overcoming steric repulsion. It's helping create tension to pull it apart. Those are all things we talked about. Acid-base covalent metal ion catalysis. We're going to look at an example of each of these with mechanisms, okay? Steady state assumption, we made a big deal out of that. Michaelis-Menten equation, why is the steady state assumption necessary for that? Now, we talked about that. It's also in the derivation, okay? The value of a Lineweaver-Burke plot seems obvious once you've got 101 versus 90 versus 100, am I guessing, right? We can get really tight numbers. Kinetic parameters, Km, Vmax, Kcat over Km, which is the specificity constant. Do you know all those, right? How is the enzyme kinetics, will it be used to provide about information about an enzyme's mechanism? Our paper will help us pull some of that out, but it's the very same things we were looking at, understanding those Lineweaver-Burke plot patterns, okay? What types of mechanisms for the body-substrate system, okay? Necessary ways to regulate them. We talked about several ways of regulating them, and that's where we're at. So then we open up and say, is it possible that this has a whole other study guide? And the answer is, yeah. Review the mechanisms, starting with chymotrypsin, ending with beta-lactamase. What does it say about the chymotrypsin and the HIV protease, though?
Those are the ones to memorize.
Will that be on the write-on?
Yes.
That again is low-level information, but what does it communicate to me when that shows up on the write-on and you don't do it?
Bad news bears.
What does it really mean to me when you come and say, Brother Bowden, I feel like that I take the multiple choice, I've studied so hard, I filled out the study guide, and then I went to take it, and I'm just not doing well, and I see that you didn't complete the chymotrypsin mechanism. It says something else is going on in your life. I'm not making a judgment call that you don't care, but something else is obviously impacting your score, because you didn't take the time to memorize what you knew you had to do. Does that make sense? Now, is that the only points? If all you did was work on that, great, I got my 40 points, but 60% of the exam is going to be down the tank if you don't study the rest of it, right? So you got to fill out the study guide. The next question that someone might ask me when they're coming to my office is, how do I improve? And when I ask them, can we look at your study guide together, and they don't have one, what does that say? I knew that was the key to the test, but I didn't take the time to fill it out. Meaning I didn't have cliff notes to study, I was just sort of a paperweight in class. Evaluate how are you studying. If you want it to improve, change some of those behaviors. If you're happy with what it is, be consistent with it. It will work. And most of you are doing a really good job. Reality, what do I expect to give? A's and B's. Right? You're already that kind of student. Sometimes we forget to do the things we know we need to, okay? All right. So we brought up these. We'll talk about all these parts here. Blue boxes, I'll show you a couple things. And so you really want to do that. So there's a lot going into this. Make sure that you're on top of that, and let's take off and see what we can learn today, okay? All right. All right, let me show you a couple other things. Okay. This is what I typically put on the exam to aid you as you go cranking through these mechanisms. There are, when we see it, you'll see there's 7 steps for the chymotrypsin, but one doesn't have any part of the mechanism. It's just the setup, and I'll show you how you can ignore that. You just do the rest of the 6. They're labeled so that it goes sequentially this way. Someone will actually do it da 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 da, and then if they're smart, they'll scribble some of this out and write in what they really meant to say. This is available also online for you to practice. Do you have to do it in my little boxes? No. I don't care if you just say, I don't want anything to, I'm going to turn over, I'm going to draw it just the way I've been drawing it on practice. I don't care, but I do expect you to have. That's actually meant to be to your advantage, okay? It says water attack, product 1, it's telling you things that actually will be to your advantage of mining. And there's the one as well for the HIV protein mechanism. So let's launch into the rest of it then. And, here we go. You already named those, right? Good. Tell somebody else that you took OChem, you know what a nucleophile versus an electrophile is. Tell them how smart you are.
Nucleophiles are electron donors.
And that's called an electrophile. Electron receives electron. They're electron poor. Electrophiles. And electron rich.
So, many years ago, I had my father's old chemistry kit that came from the 50s when chemistry kits were actually dangerous. And he gave it to me. And I would, totally not knowing anything, I was a boy, probably 6 to 8 years old, I would mix things together. And sometimes they would fizzle, sometimes they would ignite, sometimes they would do nothing. I was really curious, why does it do different things when I mix these different powders together? When I add water, why does it change what the reaction does? I didn't understand it. I had no chemistry knowledge. When we get to 105, we learn a little bit. By the time you get through 351, you're starting to get an idea. The idea is really based on what causes reactions to happen. What must be moving?
Electrons.
Electrons. Electrons moving is the driving force. And so identifying a good nucleophile and electrophile inside of your molecules essentially defines where in this molecule is it going to happen? Do I have any idea? Now it turns out that if you didn't catch what a science is the ability not to memorize facts, not to do computations, but predict what we do not know. Did you learn anything from OChem? If your answer is I memorized everything, but I don't know how to predict, ouch. Does that make sense? So we want the same thing for you. That's a hard thing to accomplish, okay? But you should be able to look at some things. So we're going to attack that question softly today, okay? Here's chymotrypsin. Remember, that's the one you're memorizing, right? Let me start by showing you a couple things. You've already seen this. What is it called when chymotrypsin comes out of the ribosome and it's not active? Tell your neighbor, you know that fact. What's it called? Yeah, it has this ogenin, but what does that mean? That's a zymogen. An enzyme that comes out not active, okay? Zymogen. Trypsin activates it and cleaves at arginines and lysines, so you can see it's cleaving right here, and it's cleaving on which side? The C terminal or the N terminal, based on the fact I'm counting 1 to 245. The N terminal, because we write N to C. Okay, so it's cleaving on that C terminal side, and then it does another autolysis where it interacts with tyrosine. Why is tyrosine important? You should already know this. We've gone over this before. What does chymotrypsin attack? The aromatics. So that makes beautiful sense. It too cuts, and we're good to go. It has some disulfides in here. That means that even though I'm doing some cutting, some things are sticking together.
Oh, so it keeps the part that's cleaved off connected through the disulfide bond?
Uh-huh.
Okay.
So it's never totally separate.
Yeah, but that's not true of all zymogens, but in this one it is.
Cool.
We didn't so much lose it all. Yeah.
Sorry, you said trypsin is what is activated?
Yeah, trypsin, which works under the same pH. Okay? So chymotrypsin has the ability to enhance the rate of a protein falling apart by a factor of 10 to the 9. That sounds outrageous until we do what? How many weak bonds would this require to do that rate enhancement? This is our predictive game. Wait, if you go up tenfold, what was the magic number we looked at?
5.7.
5.7. So I would multiply 5.7 by 9, and that would come out with some number that's less than 57 by 5.7. So about 51, right? All right, that's a fun way to do math, so that I can do that. And what number were we using for our average intermolecular force?
15.
15. Do you remember talking about that?
Yeah.
So we're going to take that 51-ish, divide it by 15. We're going to come out with a number that's between 3 and 4. There must be 3 to 4 interactions with the substrate and the chymotrypsin for it to have that rate enhancement of 10 to the 9. That was a review of what we talked about before. Okay? There's all the awesome math. It was up there the whole time, right? Aromatic amino acids, you got them? They are?
Tyrosine, phenylalanine, tryptophan.
Right. Okay. That's where it goes. It's the green spot. Okay. The red spot's for the catalytic site. Okay. The isoleucine 16 and the aspartate 194 create a hydrophobic pocket, a salt bridge to create that. Wait a second. First of all, isoleucine, isn't that hydrophobic?
Yeah. So how can it be part of a salt bridge?
How can it be part of a salt bridge? Answer that question. To your group, talk about it. How can isoleucine that's sitting here at position 13 be part of a salt bridge? 16, sorry. Sorry.
Because it's saying the salt bridge is between.
Yeah, so when it cleaves, that NH3 positives. That would
But yeah, the interaction is between the aspartate and isoleucine.
What's aspartate's charge? Negative, right? It's got a carboxylate, it's going to be negative at at this pH. What is the isoleucine's charge? Nothing on the R group, but it's N-terminus is now exposed, which means it's positive. I can't have an active enzyme until I do what? have a binding pocket for the aromatics. And the binding pocket for the aromatics doesn't exist until I do what? Cleave it so that I can have an N-terminus that will be protonated that will then stick to the aspartate.
Cool.
Re-explain that to your group because they got it, but they want to be sure you did.
Like leaving
When there's
So it's
the hydrophobic pocket. So miss it. That was it.
terminus that exposed.
It doesn't really bind to the R, it binds to
Which is why we don't want to use this portion.
So this is the right one.
So, my question is, how does this create hydrophobic?
I think it's both.
Because like, you have to get through the salt bridge.
Everybody understand how these are connected now? You're like, I turned it on because after I cleaved this right here, beautifully, I end up with this isoleucine, right? And that has the ability to do magic. Because I've now got an N-terminus where I didn't have an N-terminus.
Yeah.
And now it can interact with an aspartate. Pay attention to where the location of that binding pocket is. We're talking about aspartate 194, okay? The catalytic triad is the one that we're going to be interested there. You can see some nitrogen stabilizing oxyaniol, we'll talk about that later. The catalytic triad has 3 specific amino acids: aspartate, histidine, and serine. Every serine protease has that catalytic triad. You don't know what a serine protease is yet, but it must have something to do with serine being part of it, and it's part of the catalytic triad. It's part of the mechanism. There is one that's called other triads. There's one that uses a cysteine, where it uses actually the cysteine, aspartate, histidine, and cysteine.
Okay.
Okay? Now, let's look at the pH. I told you that these enzymes only work at a set pH. We actually looked at that in chapter 1. This is the pH it works in, which means the chymotrypsin works in which tissue? You can be specific, you can name it. The lungs?
No, it's a higher,
The
higher
ileum.
pH.
Higher pH is in the
Ileum.
Well, the tissue.
ileum. Way to go. Give that man a star. Okay, so here's the breakdown. If I'm looking at the K-cat, which is the what?
The turnover.
Turnover rate. How fast does it turn over product per second? And I'm looking at the pH. What do I want the K-cat to be?
It's maximum.
Do I want it to be high or low in order for the K-cat to mean something good?
High.
You want a high one, which means I'm doing what?
You're creating a lot of product.
I'm going to product really fast. It turns out that when the pH gets above 8, it goes really fast. But below 8, it doesn't. We're going to have to understand that. Over here, we're talking about the Km. But we're talking about the 1 over Km. If I have a Km value, what makes it a good enzyme? Low or high?
Low.
But what if it's the inverse?
So it means you want it to be,
High.
well, you want the
That
inverse to
Km would
high.
be low, but the value of 1 over a low number would be,
High.
1 over 0.5 is 2, right? It's getting bigger if I have a smaller denominator, right? This is high is good, okay? So, gosh, that sounds like a really good idea. So let's see what we can determine from this. Km's the affinity, Kcat's the turnover rate. There's a histidine that you're going to see in just a second in the catalytic triad. It's the Cato H57. Remember having to learn histidine numbers before? This is the number you want. You want H57 for the catalytic triad. And when that one gets protonated at a low pH, this doesn't work. Who's learned the mechanism? Nobody studied it?
I mean, I looked,
Gave you a weekend. And I'm sorry. You spent on another class. I'm investing. Okay, here's the other one. This one will make sense right now. The isoleucine itself, at high pH, what happens?
The N-terminus is deprotonated.
The N-terminus of the isoleucine is being deprotonated the higher the pH. Why did that matter? We're talking about isoleucine 16.
well, that's part of the salt bridge.
If that gets deprotonated, the salt bridge collapses, and that means I don't have a hydrophobic binding pocket. That affects the affinity. Now we've got to learn the mechanism. Ready? Okay, we're going fast. Life is good. This is the one you don't have to draw.
Yay.
There's a problem. This right here is only drawn in one panel, and I need you to draw it in every panel. The aspartate 102 is part of the catalytic triad, so commit it to your mind. I will write this here every time. This interaction with the histidine dash 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 is going to where?
The aspartate one.
The aspartate 102. That's a big deal. That interaction is crucial for it to have the capacity to do this. The histidine hydrogen bonds with the aspartate 102. In so doing, it's actually able to, when a substrate is in the hydrophobic pocket, it pushes that histidine close enough to do that hydrogen bonding event. And then the pKa, or the apparent pKa of the histidine, moves from 7-ish, 6-ish, it was actually 7 on the native protein, but now that there's something in it, it moves up to greater than 12. At that time, the histidine's so hungry now on the protonatable amine of histidine that it's going to attack the other member of the catalytic triad, the serine 195. So serine 195, you didn't learn any pKa values because it had to be greater than 12 when we considered that irrelevant, but now I'm telling you if I'm greater than 12, we can take it out. We can deprotonate it. So is this acid-base type reaction?
Yeah.
Definitely. There's our hydrophobic aromatic right here, and here's the peptide backbone we're going to attack.
So this second blue box over here is the first step of the 6 that we need to know.
Yeah, that's right. That's exactly right. So this is the enzyme substrate complex. Start here, write in a backbone. You do not have to do anything other than write R1, R2, and R3, but R2 has what in it?
Enzymatic.
And it doesn't matter other than that at all.
Okay.
Okay? So you can just write R1. This is just saying that amino acids to the nth. Could this have like 20 other amino acids? Yes.
Yeah.
Could it have like 20 amino acids going this way? Yeah. It doesn't care. That's what it's saying.
So do you want that whole backbone, or can we just do like?
I want the backbone because some people haven't demonstrated it. So some people get kudo points for doing it again. And some people, it'll be your first time. We need you to draw the amide backbone. It's a good time. You're going to draw it 6 times. As you memorize this random fact. Man, he's got this down.
So
That's right. Go ahead.
So it attacks the serine, deprotonates the serine, and then the serine
And then
will
it means the electrons on the oxygen that were in that bond that just got deprotonated off the serine attack the
carbonyl.
What is this carbonyl? A electrophile or nucleophile?
It's a nucleophile.
It's a nucleophile, which means that these electrons here, now that the oxygen is negatively charged, that's a good electrophile. So, and then those move down. It actually doesn't like to hang out here very long. Those electrons move all the way down here to the oxygen, which, notice this is hydrogen bonding to the carbonyl, but there's also a second glycine here, which the glycine can also hydrogen bond. So when you write it, you'll write everything you see here. Glycine 193, serine 195, histidine 57, aspartate 102, and the peptide backbone with the aromatic. You do not have to label this the hydrophobic binding pocket, but it will probably be good and wise to do that, okay? You don't have to label it the oxyanion hole, but you do have to get the hydrogen bonding right.
I just want to confirm, the hydrophobic pocket is the only region, right? Like, it's not hydrophobic everywhere else, obviously,
No, it's right there. And when was it created?
by the salt bridge.
By the salt bridge.
Yeah.
Which involved what amino acids?
No, that was isoleucine 16 and aspartate.
And aspartate what?
I don't remember.
194.
194.
Now, why does that matter? Look here again. Where are we at?
We're in the 195s, 196s.
194 is where? Between these two.
Yeah. Oh,
So, oh wait, I must be in three-dimensional space.
okay.
Yes, you are.
Okay.
And you don't have to write that there's an aspartate right there at 194, but it's there.
Okay.
Why didn't we write it? Because we wanted you to get this aspartate right,
There's 102.
because that's part of the catalytic triad.
Yeah.
Okay. Where we were at was right here. This you just saw. That was step one. Added with the aspartate. Now I come over here and I do step two. Hey, no big deal. This is stabilized by this oxyanion hole, meaning the amines here are able to help stabilize that negative charge. But come to think of it, maybe what happens if these go back to try to make the carbonyl again? Well, I'm actually, this is what, wait,
Is that tetra-
let's take a look at what, this happened, these electrons went down. This is my peptide, and where is it attached covalently to?
to that same. Oh, to the serine now.
Acid base, what was the other one? Covalent catalysis. And in order to be covalent catalysis, at some point in the mechanism, what had to happen?
Covalent bond.
I had to covalently bind my substrate to the enzyme at some part of the step. Does it do it?
Yes.
Oh, yeah. Right? So electrons move up. Now I actually grab these same electrons because this isn't stable. I've got too many electrons hanging out of my carbon. Let's pull these off and deprotonate the histidine. And of course, that means the electrons will have to come up back here so that I can have unprotonated nitrogen on my histidine 57, which is being stabilized by what? Aspartate 102. Huh. But if that happened, then what just broke off? That was all that we just learned. What now can pop off?
All of this stuff downstream.
The aspartate. I cleaved it. I literally just cleaved it. And that can float away. That was what the protease intended to do. But I have a problem. What's still in my binding pocket?
The rest of it.
It's still covalently attached.
Yeah.
I gotta get it off of there. So you draw this right here simultaneously.
In the same box is what you
Yeah,
mean?
so you've just drawn this, and essentially you just draw this right here, and you say, and this leaves, and you draw it to the side.
Okay.
And that makes step 3.
Okay. I have a question over here.
Yeah, go ahead.
So when we're drawing this out, you want us to draw that product one moving in the transition between those two states, or do you want to be involved in step 3?
You're drawing the arrow pushing just like you're seeing it, right?
No, yeah, I'm asking about the product that was.
Yeah, I would draw it right here, where it says product one and HCO intermediate. So you can draw it outside the box, or you can just draw the product separated, because it's now broken, with an arrow it's leaving, right? What must be necessary for the next step, given this? If that was your only cue card and you were stumped, what would you think?
You would have like hydrolysis.
I've got water coming in. I got water coming in. I must need water. And sure enough, that's your next step. So, next step, you see water come in.
It does the same thing.
It's taking out water, because this aspartate's really hungry, because that histidine's really hungry. Then the hydroxyl attacks, yeah, carbonyl, which moves out. Okay, you've seen this before. Is this exactly the same as 2 seconds ago?
Yeah. Only
Only
this
it's
time.
water this time instead of, yeah. Wow, that's kind of cool. All right. So, and then finally, after the water comes in, oh, this is redundant arrows. I'm going to have to get back to the initial enzyme. But if these come back now, and then this breaks right here, what was this?
Serine.
And I'm covalently attached, but now
Serine again.
I'm reprotonating the serine, and this can float away, and this is, yeah, the electrons are up there, it's not protonated anymore, that's beautiful. So now I can draw that as if that product is leaving. Okay? And that makes all of your steps. Now you guys, it's really not that bad. It looks like a lot, but once you start drawing it, you're gonna be like, I'm putting like 2, 3 arrows in and some electrons. And I'm drawing everything else the same every time. Why would I do that to you? Because I want you to look at the mechanism so I can ask you questions like, why did it matter if the pH was low on affecting that histidine, part of the catalytic triad? Why does that matter?
Because that histidine needs to be unprotonated.
If the histidine's already protonated,
You can't do anything.
it can't grab the proton off the serine, which means the reaction never starts. Ta-da! Okay. Yep, yep.
So it's just 2 tetrahedral intermediate
Yeah.
reactions back
Uh-huh.
to back, right?
Uh-huh.
Okay.
Okay. Yeah.
So do we not do that step 7 that was there?
So, yeah, step 7 in reality is the last one you're drawing with this flowing red.
'Cause
So
we're
you're
skipping-
skipping 1, you're doing 1, 2, 3, 4, 5, 6, 7. But 7, what's actually happened?
You've come up with another one.
Initial state.
Yeah.
Which is the same.
So when I have this break off, what am I really resetting? Yeah. Yep.
So step 1 is just our setup, and we draw
Yeah.
this basically every single.
Yep. Yep. You'll get it. Go ahead.
So when you draw that like last box right there, a 4,
Yeah.
7, would you draw it with the?
For me, I
still-
would not have this covalent. See this one right here? The serine's now reprotonated, the mean's deprotonated. This is here. What this is it's sitting in the hydrophobic binding pocket. And what would I do? I would put an arrow that says
It's like, it's gonna leave.
leave.
Yeah.
Okay, cool, so you just draw like, it leaves, and then that's it.
But I would put the arrow that says this is leaving now, because I can see it's not attached anymore.
Yeah.
So is there something that's gonna make it leave, or does it just eventually dissociate?
Yeah, great questions. And there is a reason to leave, but
We don't need those.
We're not gonna get into it?
yeah.
Okay.
We're gonna, this is the inhibitor, I'm not gonna go through it because we're behind, but I am gonna look at another acid-base catalysis reaction with hexokinase. Does anyone know hexokinase? Have you heard of that enzyme before?
It's part of glycolysis, right?
It is part of glycolysis. It's actually also part of the pentose phosphate pathway. It's also part of creating of glycogen, meaning it's the first step when sugar enters a cell that happens for multiple pathways. But we usually associate it with glycolysis because that's the one we memorize. But it's actually going to multiple pathways.
Cool.
That will help you when you get to metabolism, because someone will assume that you can understand what I said. Okay? Why would I put a phosphate on a sugar if I wanted to keep it myself? It's costing me an ATP. Why would I do that? Tell somebody else.
Doesn't it make it so it can't if it stops it from working?
It's charged. That's even wrong.
Yeah. Just like.
Was your neighbor smart? Did they say something like, if it's charged, it won't cross the membrane? That means I just claimed that sugar for myself?
That's my groupie.
That's the way to go.
He said that.
All right, so you notice magnesium's associated with that? That's kind of cool too. All right, so this is unbound and this is bound, and I'm going to put both of these in here and I'm going to make the reaction. We call this reaction an induced fit. Xylose and glucose look what?
Pretty similar.
Yeah, in fact, it's only missing what?
Another carbon.
Another. Yeah, and it would work. Turns out that if I throw xylose into hexokinase, it will actually phosphorylate water.
Because it'll grab the water as its last bit that it's missing or something?
Yep. Would that be really healthy for a cell?
No.
Because I'd spend all my ATP doing what? Phosphorylating water. That
So would xylose leave, or would water just keep kicking out? And
water just keeps kicking out.
Well, that'd be easy.
Yeah, it'd be right back. Yeah. Okay, you remember I said I was going to give you a tack? Okay, for the next 3 minutes, I'm going to give you something beautiful. Here's aspartate 205. It's negatively charged. You see that?
Yep.
This is ATP. Magnesium's up here. This is glucose. I want you to propose where. You know it must involve the enzyme, because I put sugar and ATP together. They don't just magically go together. Give me an idea of where the first arrows would go. First step approach. What do you think's going? Try to give me a guess at a mechanism. You got the next 3-4 minutes. Just get going.
Electrify the tires. Hydrogen on the glucose.
This is the question that you've never been
There's
asked.
also an YouTube class, I don't know about it.
Don't bring that up.
Sorry.
Son of a far away.
I don't know if they retrieve that first.
Well, I'm also just kind of thinking about.
Yeah, I can see that.
The aspartate is negatively charged. These phosphates.
What do you guys think?
We thought it might mess with the magnesium
Really? Oh, because it's phosphate.
or mess with the hydrogen on the glucose.
I thought maybe you would go on the primary alcohol. On the glucose first.
By the way, it might be helpful to know that the product that it's going to form is glucose 6-phosphate.
I still think so.
So the phosphate's going to go on which carbon?
Sixth carbon.
Which opens up the sugar.
But like that was like from OChem, the weaker acid is that alcohol already. It's like it's already there.
The sixth
So that's why I didn't know if
It's
it
an
was.
alcohol.
Oh, you're right. The sixth carbon is already available.
Wait.
It has a pK of
What was the product again?
What? What?
What was the product?
Glucose 6-phosphate.
6. We gotta have phosphate attached there. We gotta depronate that alcohol though on this side.
So unless it has a residue,
Oh, sorry.
though,
Okay, so
Like you could have residues that change the pKa of that aspartate too.
Oh,
And so
yeah.
upping its pKa
That's true.
and pulling it off.
And carbon.
That
So you
hydrogen
think
off.
that it would attack the magnesium because it is positively
Some
charged,
phosphate
and
attack
then
Well, I don't know what the magnesium is doing. It's just holding those like.
well, but if it did that, then it would have to pop
With
off,
the-
and then the oxygen would be negatively charged and then attracted to the hydrogen.
Would the phosphate attack carbon 6?
The phosphate?
Would it attack carbon 6? After the alcohol is.
Okay, let's take a peek.
No golf.
3-4 minutes has gone by. How do you do?
Ideas.
Okay.
Oh my gosh.
If you started with the ATP, you're thinking life is good. But if you started up here with electrons being negative and went down here, that would suggest I didn't need the enzyme. I needed the enzyme, so these electrons came over here. Now, if they went off to get this phosphate, that would be a feasible mechanism. They could have attacked right here, right? If you proposed that, you were still good, but this is the way it goes. Electrons attack, deprotonate here, okay? Which means this is what? Negatively charged, which means that these guys do what? Attack the phosphorus, which means I got too many electrons, which means that it brings those over to the oxygen, essentially cleaving this off, and I'm set to go. That's the short answer of what you need to know. Now, you need to memorize that mechanism? No. But the real question was, could you have identified the electrophile and nucleophiles that were at least targets? If you can't at least identify the targets, then maybe you should be reviewing a little bit of your OCHEM, okay? Because that's really what we were saying. Do you know what electrophile and nucleophile is? So that I can take my dad's chemistry set and guess what might happen. All right. Yes, I've taken advanced virology. I know all about it. I know all about HIV. We did research on it in my group too. It's awesome, okay? Somebody give me your knowledge of the 3 targets of HIV. You've got a reverse transcriptase, integrase, and protease. You not there yet? Okay, you got it.
Okay, so reverse transcriptase is going to change your viral DNA back into effectively the same
Nucleotide
nucleotide code as your DNA of your cell. Your integrase is going to clip and attach your DNA into, or the viral DNA into the host DNA, and then your protease starts working on proteins
Okay.
formation.
So one, to take the code that's just sitting here from this inanimate object that we don't call alive, but this random code, and turn it into something usable, to actually then come out and to integrate into your own DNA. Isn't that nasty? By the way, it stays there. Never leaves. And then what happens to that is we have to take the protease. What's the protease's job? It's actually, in this case, it's producing a whole bunch of proteins that the native cell does not have any recognition of. And it's going to come over there and it's going to cut it so that it assembles a viral capsid, so it can redo it again. So those are the 3 targets. Ours is the interest in the viral capsid protease for this drug approach. We have targets for all 3 of these. We're interested in the protease mechanism. Here it is. Look at this, 2 minutes and we're going to go right through it. That's how hard the other mechanism is. What amino acid must this be?
Proline.
And is it in an amide backbone? Oh, good, you can draw that one too. What's this? Phenylalanine. Oh, great. This is a what?
Water.
And these are,
Aspartame.
wait, is this a typo? This is a dimer. An identical dimer that has aspartate 25, aspartate 25. This one, coincidentally, is deprotonated, attacks and deprotonates the water. Now, water's not happy,
Accessing a base.
good nucleophile goes right after the carbonyl, really the backside of carbonyl, right? And then brings the electrons out front. Okay, does this now covalently attach here? No, okay. But I am now in a good position that I can actually take these electrons, which were out on the carbonyl, back to the center carbon and take off the nitrogen and attack the hydroxyl, deprotonate it again, and I've cleaved it. Wow, that was simpler.
This would be like a hydrolase, right?
So what would you be drawing in the 3 boxes you're provided?
Everything.
Everything you see there. What is the squiggly line? What is this going to?
Dust.
Extra amino acids, right? Okay. So, here's the mechanism. Life is good. By the way, as we close today, knowing this gives us the ability to do this. Wow. What do I want to mimic? According to the stickase model, what do I want to mimic with my inhibitor? What would bind the best? The transition state. Instead of the native substrate, what if I could bind the transition state? What if I could bind the transition state and not let it go to product? That would be awesome. That's what we've done here. Okay? All right, you guys, I will see you on Wednesday. We are moving fast.